Thank you. Take two. Yeah, thank you. Just to give you the impression of how hard I still find all of this to even understand how we can solve it. I had a minor meltdown all last night, and I think I understand again this morning that we can actually make some charts, but it was touch and go. But I should actually tell you why we need some charts and then how we do them. And I'm not going to get you into the complete technicalities of that. So sort of recap from what Dusa did and sort of application for genus 0 1 point Gromov-Witten. Right, let me assume that we're in the nicest of all possible cases in which virtual transversality is really actually not needed, because I'm going to assume that there's no bubbling and no isotropy. So the holomorphic curves of a fixed non-zero homology class modulo the automorphisms of S2 that fix infinity. I'm going to assume that this is compact by itself and contains no multiple covers. Right, and that by non-trivial unique continuation, that means that this automorphism group actually acts freely. Right. So at least in that case, we ought to be able to regularize the Gromov-Witten moduli space. And the Kuranishi regularization now would require, according to Dusa's and my latest theorem, a weak and, well, hopefully additive. I'm not going to sort of impose that from the beginning on my construction. Kuranishi structure. For this guy, so what does that? It requires actual hands-on constructions of several things. So A, we need basic charts. Following Dusa's notation, K1 up to Kn. And I'm going to say explicitly how to do that, but I just want the summary here. And we're going to need some charts Ki and transition maps between all the sum charts. So that's what we need to construct, and then we should make sure that they satisfy various requirements. And I'm going to sweep those under the rug. Except for when I'm telling you that there's no other way to construct this chart but somehow, well. So, and in particular, what I'm going to do is really just think about two Kuranishi charts, K1 and K2. So maybe n is equal to 2. And then all that I really need to construct here is K12 and maps phi I 1, 2 from Ki to my K1, 2. And I would not need a cocycle condition. So this is going to be hard enough. And I figure, let's see. Yeah, right. I'm going to switch blackboards. So I'll start the construction on this board. Hopefully this works out good. Okay, so, right. There's going to be a little cabinet of horrors on this blackboard. So this is the idea of sum charts. But let's forget about this guy for a start. Let's just think about two charts. So there's, bundle, your vector space over an open set in Rn. Here is your open set. Vector space is, I don't know what, maybe one-dimensional, and you have some terrible zero set here. But the good thing is it's a model for the terrible zero set in your singular moduli space. And you have another one, so that would be E1, B1, and S1 here. Right, again, something cuts out. You have a zero set, have a homeomorphism into there. Right, so these two now have some overlap, and so they overlap in this triangle where it's sort of an open set in both these charts here. And then they have squiggles, and there's special extra intersection down here, just so we can have some fun with that. Right. So right now this space lies in the plane, and so you'd think I could just map these two spaces in there and have a nice transition map directly from here to there. But this space lies in nothing other than some large space of maps modulo reparametrization, and that is not a good space. And so there's really no ambient space a priori through which this transition map could go. So plus so we know how we want to glue the points. I mean, this point here came from some point here and came from some point here, so clearly we want to map here to there. But a point here goes nowhere here, because psi1 is only defined on the zero set. So there's no direct meaning of that over here.
You could say again, you need a map from where to construct a map from where to where exactly.
Let's assume Dusa didn't tell us what a sum chart is yet, right? I would need to say what it means for these two charts here to be compatible.
Yes.
And of course, I have, I mean, on the footprint, they intertwine. I mean, right? There's a homeomorphism here, there's a homeomorphism there. I can compose the homeomorphisms. I get a homeomorphism from the zero set here to the zero set there. But somehow I should now say that this homeomorphism extends to something on some open subset of the B's at least, right? And then I should maybe say that that's differentiable or something, right? So I would want some sort of differentiability in my transition map here. And there's just no meaning in which I could relate this point to some point over here. So the way to do that, sort of talk about meaningful relations, is to say there should be another chart. So this here is this is a larger base, 0, 1, or 1, 2 up here changed into 0, 1. Right? And from the zero set in here, there should be a homeomorphism to the overlap of the footprints up here. Right, so that's the green guy. Right, so now I have a chart for that overlap. And now I'm going to say that these two charts are compatible if I can embed the entire base, or some open set actually. So there's some open set in B0 that I can embed in here. Right, so in this case, here's an open set. And it gets embedded into an open set here. Right, so you want to this is two-dimensional, so this is an embedded two-dimensional submanifold in this three-dimensional space. Right? And so I'm going to do the same thing with this chart here. So another open set in B1. Right, I don't know what. Right, so now it's already interesting to see how these guys will need to intersect here. Right, I have this two-dimensional subset here that is intertwined by the footprints, and so that forces these two embeddings to be parallel on this triangle. Right, so there's some domain where these two embeddings are absolutely not transverse. Right? So you have agree, yes, yeah, I mean tangent. I mean they agree, right? Yeah, and so their tangent spaces are the same rather than transverse, right? But then I have this. I drew this other little one-dimensional piece where, generically two embeddings would intersect transversely there, right? So. So the two embeddings could intersect transversely here, parallel up there. No idea, Worse, they could intersect and, not connected. Yeah. No, it only needs to contain. Actually, right. It only needs to contain the overlap. Right. So this green stuff here. It actually needs to be exactly the thing that's contained there. Right, so I made a mistake here. Because the overlap does not see this forking point. So actually, what's happening here is that this neighborhood cannot go to the forking point, to that branching. Make sense? Okay. Good. Okay. So, right, so that's the idea of a sum chart. So somehow we need a larger chart into which we can embed both of these domains. I do want to sort of quickly add a little more horror here, which has nothing to do with Gromov-Witten, but just the question of how do we construct a virtual moduli cycle from a situation like this? Right? So we would like to start regularizing this by perturbing our sections. And would like to argue that it might be possible to just start in this chart and then work your way up, but you certainly have to be very, very careful. So if you started in this chart here and you perturbed, try and get this guy transverse. Right, so B0 is an open set. Yeah. 0, 1. Oh, there's no 1. Okay. Twiddle. Yep. Good. Okay. Okay. Good. Thank you. So, I'm just going to go ahead and perturb this guy. So, right. I could also let me add a little more horror here. Nobody tells me I can't have sections, more section here. It's sort of pretty close to the boundary. So now I'm going to perturb this guy. If I just perturb on that space, so a couple of things could happen. I could get this triangle certainly is going to need to become one-dimensional. Say 1 is actually my dimension. But nobody tells me I can't get sort of a branching point on the boundary. And then, well, okay, yeah, something here. Here, I know this boundary point is sort of tied in with the rest of the space, so I'm fine having these boundary points here, because I'm going to keep dealing with them later on in the later charts, right? So note, right? So goal is that somehow the union of all the S twiddle I inverse of zeros modulo transitions should be triangulable. So in particular, it better be closed, so no boundary and compact. And if it's triangulable, it's also better be Hausdorff. So this boundary point is fine. That's not going to be a boundary off this, because it's going to get dealt with later on. In fact, I'm going to need that guy. Still, there's a boundary point here. Well, now I'm going to need to use something about topology, right? I have no idea where that's going to go. So already somehow this was not a realistic picture. This is going to be a one manifold. I don't really know where that's going to go. Maybe here. Even worse, right? And if I'm not incredibly careful out here, I could pick up new boundary points that I'm not dealing with later on. Right? Because there's no overlaps here. So, yeah. And if you read the standard literature on how to do this, I don't see them dealing with this ever.
Okay, so you're talking about Kayano.
Yeah.
The approach in the Indian is that you take these two bundles as essentially trivial. 0 and 1.
Oh yeah, they are trivial.
So essentially approaching the Indian, you take the sum of these two bundles.
That's about constructing this. Yeah.
So let's say you take the sum of these two bundles and you map the whole thing into your abstraction bundle over on a neighborhood with 0 set.
Yeah.
So you can glue your P0 and B1 using this. Over that you take the sum of the two bundles and you map that into the abstraction bundle where the section sits. And then you take the pullback of the 0 set, which now sits into the sum of the two bundles. And inside of that, you perturb the section inside of this.
Here.
What?
So you perturb the section only in the sum bundle.
You perturb a section over essentially over B0 union B1.
Right. So I think what you're saying is you build a virtual neighborhood, and that's of your unregularized space, and you perturb your section in there. Yeah. Right. So that means if you want again, then. See, the problem is what you're going to get is you're going to get charts, and you're going to get transition maps that satisfy the cocycle condition. But that does not imply that the space you're getting is Hausdorff. Unless you cut it out from a Hausdorff space.
Point. I mean, when you put B0 and B1 in the sum chart, they don't intersect transversely because they're intersecting along X. And X, of course, doesn't have to be a manifold. It can be really horrible. Yeah. So even if it's sort of locally one-dimensional, they're intersecting non-transversely. So if you build a section over B1 or B0, and then you restrict restrict it and sort of transfer what you've got to the overlap, and then try and extend. You may not be able to, because it may be that it's defined on the image of X, the 0 set in B1, and that's not smooth, and therefore there's no smooth extension of that. Now, I'm going to tell you how to resolve that. I mean, I was going to actually point this difficulty out at the end of my talk and say there's a way of resolving it. I mean, it's just a manipulation of the cover, but, you know, you can't just take this cover and what you want to do is operate in chart, build something over B1, transfer what you've got on the overlap to B2, and then extend. You can't do that. You have to be a little bit more clever, because the overlap of these charts is not smooth in the space they're sitting in.
Yeah, let's yeah, we'll get there. I just figured, you know, so my point is just, you cannot start in a single chart and do something easy that's not going to get you into trouble later on. Right? So, you know, you have to, in the first chart, you already have to take account of all the overlaps later on. And you do need to do some shrinking, and, you know, and that's, I don't see that anywhere in the literature, that you just sort of, the construction chart-wise, taking into account of, you know, the Hausdorff requirement and the closeness and compactness. So. And the smoothness. Oh, yeah. But I will construct B01 for you. Yes, I will. But first, I want to get an analytic horror cabinet on the board to know what I should. Huh? Yes. Yes.
5 minutes to 9.
Ooh.
Why don't you omit your analytical horror cabinet and do
I have 35 minutes.
Okay.
Don't worry. So using your favorite Banach norm, for example, Hölder or Sobolev. A couple of things are just simply not differentiable, or not C1. So, well, let me actually, so, right. So the first guy that's not so good is, yep. Okay.
So I could think of having the smaller dimensional piece stuck into the larger dimensional piece.
Right.
Now, if I, on the slower dimensional piece, of course, I make a modification. It goes into the larger piece. And if there's another smaller piece going close to it, then I already run into trouble.
I'm screwed. Right. That means we need to, I mean, that's another combination.
So you have two things stuck into the larger.
Yeah.
If you go too deep in, you already are in trouble with whatever you want to do.
Yeah.
I mean, they're intersecting in the 0 sets, which you just have to assume is an arbitrarily horrible compact set. I mean, you know nothing about it.
Yeah, I mean, I should say there is, I mean, that's what the good cover in Fukaya Ono is about.
Once you take all
But
this stuff away, then actually I think you actually have a finite dimensional polyform.
well, but my point is that even if this is a good cover, you cannot just perturb chart by chart and know that you're not screwing up your Hausdorffness. So this is your reparametrization action here, and I've made a point of writing it as an action on smooth maps, because that's what we think are holomorphic curves, or perturbed holomorphic curves should be smooth. However, the smooth maps are just Fréchet manifolds, and if we want to do any kind of implicit function theorems or Newton iterations, we need Banach norms. So we'll need to give this some sort of Banach norm, but this will not be C1 in any norm that I know of. The only way of making this C1 is, to the best of my knowledge, to restrict within the smooth maps to a finite dimensional submanifold, because then all norms are equivalent. there is sort of a little secondary horror, which is part of the actual transition map between slices. How do I, right. No, sorry. So this implies that you have the same problem with the transition map between slices. If you have, let me sort of not write this precisely right now. That's the notation I had yesterday. So F, what was that? How do I want to do that later on? F2, right? So these are local slices to the automorphism action, given by hypersurface conditions transverse to a function F2 or to a function F1. Right? Somehow different slice conditions, and the transition map is U goes to U reparameterized by something which depends on U. Right? So the picture here is, if these are your orbits, there's one slice and another slice. Right? So, you want to map from here to here, right? You can go along the orbit, but the amount that you go along the orbit is going to depend on the point, quite obviously.
So these are local slices.
Right. Yes.
And F1, F2 are what?
The base points, right? So F2 is here somehow, F1 is here. And I'm gonna write them down precisely. Right now, I should do this. Okay, so BF2 is all the maps that are approximately equal to F2, and that at 0 go through a hypersurface Q2, 0, and at 1 go through a hypersurface Q2, 1. Right, so you see so this transition map you can factor into the action and into reading off gamma u from u. And it's not just this action that's a problem, it's also reading off gamma u that's a minor problem. So, and again, this one we can factor into 2 steps. First, we read off where my u actually does intersect the hypersurfaces. So u inverse of Q2t. And I always write t for t equal to 0 and 1. So those are points on S2. Right. And once I have these 2 points, I can read off gamma u, which is now just equal to gamma w, by asking that gamma, what exactly, I always forget. Gamma w of 0 needs to be w0. Gamma w of 1 needs to be w1. So from here to there, that is perfectly smooth. Right. But this map here is only CL with respect to the CL norm. Right? So yeah, it's sort of a case of scale calculus might help you here. But so that's, if you're fine with getting sort of CL manifolds, you could work with this map someplace. The problem is we'll also be iterating things, and so I don't know what happens when you intersect CL manifolds, and yeah. So we decided to try and stay away from partial differentiability. So we're going to try and not use any of these maps other than this one. So yeah.
So your second point is how to associate to a map the corresponding automorphism,
Right.
which we need to represent.
Right. Exactly. Yeah.
But even if that is CL.
Oh yeah. You.
But then afterwards you want to use that automorphism to reparameterize.
Exactly.
You lose all differentiation.
Then you lose. Yes. Yeah.
So
Yes.
somehow,
Right.
yeah.
Yeah.
So you're not saying you could make it some finite CL. You cannot, because you still have to reparameterize.
Right. If you view this, you'll hopefully see how we can decouple the two effects. We're going to decouple U and W, and sort of view the reparameterization. So we're going to decouple. So U and W are going to become independent variables, and then composition of U with gamma W is fine if we keep W fixed. Right. So that's all right. So let's see. Basic charts. Okay, so A. Let's see. Maybe, so I'm going to try and squeeze a lot here. So A, we'll need to choose things. And that's almost all the choices that we're going to be able to play with. So we're going to need, well, base points in a Dillon-Mumford space. And we're also going to need representatives of those. And then for each one of them, we're going to need slice conditions. So those will be Qi, T, well, 0 and Qi. 1, 2 small hypersurfaces in M, transverse to the image of Fi. Are the transversal constraints, right? Yes, sorry, right, yeah. And we need obstruction spaces. EI, so representatives of the co-kernel or larger, so they should be in W1P of S2 values in 0, 1 forms of F, Fi star Tm. So that's just spaces there. And these spaces will need to extend somehow. And to finite dimensional bundles in the union of all U close to Fi. And I'm going to sort of, this is sort of a pretty abstract, I've already sort of dealt with my automorphism action with some geometric idea. And now I'm going to sort of start with abstract obstruction spaces, and I'm going to try and see what I need those obstruction spaces to satisfy. And the upshot is going to be that I need to also construct these geometrically. So this is essentially the data that I'm going to get to play with. And now, right, my basic charts sort of fairly simple. Let's see. Right, Dusa would say I want an open set in some RK and a trivial bundle, right? And then, hold on. The bundle is the other way, right? This is already my section. And then I have my 0 set. actually in RK, and I would like this to embed to my space that is supposed to get regularized. So I'm going to I would like that too. The immediate construction is going to be by trivializing a bundle. So this is that extended obstruction bundle, and it's going to get restricted to some finite dimensional smooth manifold, hopefully. Namely, all those maps that are W2P close to Fi satisfy the d-bar equation up to this finite dimensional vector space. So this is the fiber over U here. And I would like them to satisfy my constraints. Right. Now I don't have to divide by anything. This is a little bit of a troubling equation because I'm evaluating U at a point that might not be so terribly smooth. But I'm not wiggling the point. The point is fixed. So this is a smooth map. This is a smooth Fredholm operator. And, well, again, so now the question is it transverse? Right? Of course, if I pick this large enough, certainly it's going to be transverse. And if I take these out, it's if I just used the obstruction space as perp to the image of df, then certainly this equation is transverse. Right? And then I need to use my knowledge that it actually, the kernel contains the tangent space to the automorphism group. And so that tells me that then this equation is still transverse. Right? So there's already here, this is not totally trivial to argue why this is a smooth manifold. Right. Okay, but we can do it.
How important is that? I mean, could you just ignore that for a second and just say, well, at most it adds fine dimensional cokernel again, this condition U of P, and then you might the EI is a little bit larger.
Yeah, fine. Yeah, you could take your EIs just larger.
Okay.
That's yeah. I'm just saying. It's actually true, but but if you want to somehow make these obstruction space sort of a canonical choice, right.
If you wanted to globally, sometimes people want to globally cut down the moduli space by obstructions in order to get a zero-dimensional solution space. So then you'd have to, you wouldn't necessarily have transversality there. You would have to add extra things to be you could cope with the lack of transversality. But I mean, you could do that. You could build that into your domains. But we were sort of doing the
Oops. So, yeah. Why is B finite dimensional? Yeah. I don't understand. Where is your equation? Old type quote of Gromov's when Pandari Panda was defining Gromov-Witten invariance. I don't understand. Where is your equation? Right, so in this picture now it's really easy to get the section. I have U, D bar U is in my bundle. I just map it to D bar U. It's in that bundle. Right? And so now, I'm just going to take a small neighborhood of Fi, which is isomorphic to what? A small disk. And I'm going to trivialize my bundle over that to pull everything back over here. And also here, obviously, right, so D bar inverse of 0 now sits in there and maps here, right? So, and this is important. This is a homeomorphism now because we knew that the local slice conditions cut out, are a homeomorphism, right? So U going to equivalence class of U. And I believe that really here we're using somehow the fact that this local slice somehow in infinite dimensions gives you a homeomorphism. Okay, so that's your psi. Why mapping U to equivalence class of U, right? You want that to be a homeomorphism when restricted to here, right? And I believe the only real proof that we have is to say, well, you know, if I could forget about this equation, then there's a homeomorphism from this local slice to maps modulo the reparametrization. And this is just a restriction.
So you're using the automorphism action.
Yeah, it's continuous, right. I'm using continuity of the automorphism action, and I'm using that. I know that this infinite dimensional slice is a continuous slice. Okay, good. Now let's see whether, oh goodness, can I squeeze B12 on the same board? I can try. Oh, wait, is there board behind this? Probably not, huh? No. Okay. Let's see whether I can. Let's see. I could delete the top. That is kind of true. Yeah, let's do that. So we need the sum chart now. So let me just give you immediately, you know, the thing that we believe actually works out, rather than showing you that there's really no easier way. So somehow, in some sense, I would like this bundle here to be some sum, or something larger. So at least it needs to contain this sum in some sense. We'll see what that actually might mean. And I would like, again, my section to be the d-bar operator, and I need a larger thickened up moduli space, or thickened up sort of perturbed solution space. And, well, so the idea here of decoupling the equations is to just add marked points. So smooth maps times S2 4 marked points now. And I would like this to somehow be perturbed holomorphic. And I would like so these marked points here, U at these marked points should lie in my slicing conditions. So that's my transverse constraints. And now I still have an action of the automorphism group left, right, by simultaneously reparametrizing U and moving all the marked points. So that's not good. We're going to need to pick some local slice, but now it's really easy to pick a local slice. I could just fix 2 of those points. Okay. So really, the way we construct a smooth structure on here is to take U and sort of think of this as 0, 1, and then really I want to just call these guys to W. So we just have 2 points now. And now I'm going to sort of become a little more specific here. My bundle is actually going to be a bundle over the maps and the marked points. Okay, so so the problem is if I now write down this equation here, so there's some equations that are okay. So I need u at 0 and at 1 to satisfy the slicing conditions of the first chart 1. That's an okay equation. The equation that's not okay on this infinite dimensional space is u of w 0 and 1 lying in q2 0 and 1. So this here is not, this is only CL if, well, it actually, right, with respect to CL norm on C infinity. Right? So I don't want to immediately impose this and try and, this here is not a smooth Fredholm operator. Right? So I'm going to forget about this finite dimensions and first make this space here. So actually this is sort of a B hat 1, 2. And then my B1, 2 really is going to be a subset of this. Namely those that, so after the fact I'm going to impose this condition. So, right, so this is now going to be a smooth Fredholm operator. Well, it's Fredholm because it's on finite dimensional spaces. And it's going to be smooth because I'm in a finite dimensional space, and hopefully I've made sure that all these here actually, so I would like to make sure that this solution space actually lies in the smooth maps. So then this is a continuous equation, smooth equation. So that's somehow the decoupling magic that's going on. Right. Does that make sense?
You choose your reflection bundle consisting of smooth maps.
Right. Exactly. Yeah, that's
You have to choose it regularized.
right.
Because
Yeah.
Originally also define it on bad points.
Yeah, you better say what E tilde.
Right. I'd better see what. Right. Yeah.
You don't want people to.
Right. We're gonna. Yeah. Okay.
It has to be regularized.
Right.
Yes, it will be.
It will be.
It will be, yeah, but
Right.
But that is how you have to choose it.
Yeah. So
That means that, so
here are my choices still. Okay. So that was the, well, modulo telling you what this bundle actually is. That is going to be a new Kuranishi chart. Right. But we don't know what its footprint is yet, and we don't have transition maps yet. There's one simple transition map, so B1 simply goes into this by mapping U to U and the pre-images of the slicing conditions for 2. Right. And since this is in finite dimensions, this is again a smooth map. So that's not so bad. Right. But now, this worked because this U is in the same local slice as the U's here, because this is your local slice for B1. Right? So now I would like B2 also to map into there. And I'm going to call these V. So what would that map look like? Oh, of course it's not, sorry, it's of course not the whole set, right? So there's some open set inside here, yeah. It's also close to wherever my intersection is, right? So, right, so these guys here now need to map up here. In particular, this is in the local slice for the Q2s, and I need to get into the local slice for the Q1s. Right, and then my marked points are going to be gamma V inverse of 0 and gamma V inverse of 1. Right, because that's where I had the local slice conditions for Q2. And now the beautiful thing is, like, if I call this here W, then gamma V is actually determined by the points W. Right? So all I need to solve is gamma W of, this is sort of W0, W1, this is my pair W. I need gamma W of WT to be T. Right. That's the map that's smooth. Right. This is the good map. Right, because it's just between finite dimensional manifolds. Phew. Okay. So E twiddle 1, 2 is essentially determined by this map actually landing in this space. Right? So, right, so now we need V composed with gamma W and this W to, well, be in B1, 2, and that means that I'd better have D bar of V composed with gamma W in this fiber over the pair U, oh God, what is that? V composed with gamma V and the point W. Right. So this is, well, D bar J V composed with D gamma W, right? And this here, by definition, we know is in the fiber of E2 over V. Right? Okay. So, but really I want to define this fiber. So I'm going to call this here U. Right. So what I need is, right, so my fiber E twiddle 1, 2 U comma W. Well, it's certainly, so in order for this here, I need E1, the fiber of E1 to be in there. Right? So that's the transition map from B1. And now I'm also going to need this pullback. So I need the fiber E twiddle 2 over V now is U composed with gamma W inverse. And then this entire, every one form in this is getting composed with the differential. So this is base requirement for the construction of our transition map, our sum chart. Right. And so, let's see. What we're going to do is we're going to just define this by equality. Right. So be exactly this space, right? So far that is a collection of subspaces parameterized by pairs u, comma, w. And so now this needs a couple of conditions on it so that B12 is actually a smooth space. So, or the B hat 1, 2, right? So how do I know that this is a smooth manifold? So the choice as taking the sum here comes from us really wanting it to be additive. There's a question of whether one could just sort of take something larger if this is not a direct sum. But to be honest, I don't understand how you take sort of random families of vector spaces, of not vector space, right? You're not in a trivialization here. This is random this is two random finite dimensional sub-bundles over Banach manifold. And I don't get how you make that sum sort of, how you soup it up to something finite dimensional. You know, there might be something, but it's certainly not trivial somehow. So our first requirement is that E twiddle 1 over every point is actually intersects these reparameterized guys only in 0. For all u and gamma that are somehow relevant, that are in the overlaps of these charts. So then at least we have a direct sum here. And that means we have, a bundle of constant dimension, right? We have a family of vector spaces of constant dimension, because now the next thing is constructing things by reparameterization here. And this is going to be, in order to make this a Fredholm problem, we need to do this over some Sobolev space of maps. So we need to do this abstraction bundle over that Sobolev space of maps. Right. And so that means this here, not a good map. Because W is going to vary here. U is not smooth. Even if U was smooth, if we took some topology on here, this would not be a C1 bundle. Right. So we need a very special bundle. And I would like to think of this as a geometric bundle of actually each of the E twiddle i's, right, such that this form E twiddle I U composed with gamma inverse is smooth. And that's right. Well, Liu Tian give us a good construction. Which is right. Let me give you the rest of the list of requirements, because I'm not sure this is terribly instructive. So the other thing that we need this very special geometric form to do is we need this B hat. We need the perturbed solutions to be smooth. Right? So that means all these guys need to be somehow smooth. And this is something I haven't argued about because we didn't do gluing. There's 4 points here, right? And you're quotienting out. This really smells like Dillon-Mumford space. And in order to do gluing, we will need to lift this whole construction to construction on Dillon-Mumford space. You're only in Dillon-Mumford space when these points are not equal. And so we know of no other way to get into Dillon-Mumford space than to just make all these slice conditions disjoint. Right. So So what that means, if someone gives you a perfectly nice set of slice conditions and obstruction spaces, and you make your basic charts from them, and they're nice basic charts, and maybe you've even made sure that all your perturbed solutions are smooth and your bundles are going to transform nicely. In order for the charts to have a chance of being compatible, you need them to be summable. And in order for them to be summable, you need this transversality, overall overlaps, and you need to like puncture your slice conditions to get into the Mumford space. So right, so somehow summability requires, I would call this transversality of the basic charts. If you have two charts, maybe, but there's a lot of charts, and so this. And I thought there was I saw the structure, and I think it's doable, but it certainly requires some headache. But this is also just sort of conceptually, sorry, let me say this. Conceptually, this was the point when I stood up and ran out of MSRI and said, I am disgusted. Because regularization should take care of transversality for you. You should not have to make some sort of transversality in order to get to give a space the structure in which you can regularize. Right? I understand that this is a lot easier to achieve than to just take the whole Deligne-Mumford the whole Gromov-Witten space and make it transverse. But it's still some non-trivial amount of wiggling going on here. So, okay. You don't get into Deligne-Mumford space. We don't know how to make some charts over near nodal curves.
The thing is that we want to have a very canonical construction, so that once you, the idea is once you've got the basic charts, there's essentially only one way to sum them, modulo the choice of the domain. But, it's all canonical. And then we do it by a very nice sort of pullback construction over the Deligne-Mumford space. But then you really want to be in the Deligne-Mumford space. I'm sure there are many ways you could do this, but my idea was I'm not so horrified by Katrin as sort of taking a set of data and making it generic so that you can then do it properly. So that was the idea. Take your basic charts. Each of them can be perturbed a little bit because, everything is... So you just perturb each of them a little bit, but you have to say exactly how you do it, which is not so easy. But you can do it. And then you have this finite set of basic charts, which are all generic, and then you can just sum them, and there are no choices in the summing construction except for the choice of the domains, exactly what that B1 hat, 1, 2 hat is.
So you're basically saying all these tests either have to be completely different or completely the same.
Yeah.
If you
Yeah.
the same, we'll give you the same chart.
Right.
And
If they're different, then
they have to be completely different.
Yeah.
That's kind of
Well,
big jump.
the thing is that there are many ways you can do this construction. What you don't want is sort of indeterminate things where the intersection is not transverse, where they're the same.
Intersection was not.
Well, if you just have one place where the sum, typically if you take two finite dimensional bundles or sub-bundles, there could well be one place where the rank drops of the sum. That would be sort of bad news. Because you might not.
So the reason you want this condition is so that you can take the same bundle over the entire intersection.
Exactly.
Instead of taking a small cover.
Yeah.
Instead of taking a cover by small set.
Yeah,
No, but even if you take a small cover by small sets, you still have to have some bundles on that.
Yes. But then when you
And then you just have, what you're trading for is you're making the set, you make capital N larger, and you make the domains on which you need the transversality smaller. But it's still, it's still a large number.
We wanted to have something where we had absolute control over the domains, because having control, knowing exactly what they were, means that we could do what I'm going to talk about and make household medicines, or we could work with them. So you have to give up, you have to start with things which are sort of disjoint and generic, and then you completely understand what they meant and what each was.
Yeah.
I think having them disjoint, meaning these points on the sphere coming from different charts being distinct, shouldn't matter really. Because I think what should matter, you may have additional marked points which vary in the linear Mumford space, and of course these additional marked points giving you constraint should be different from your other marked points at which you evaluate.
Well, let's actually let me.
Say these 2 points, D0, D1 from one chart and D0, D1 from the other chart, whether or not they are equal, that should.
That's what. Hold on. Let me stop, please. Let me say 2 more minutes. I think I can at least make you worried. Right? So we need, anyways, a special geometric construction. The only one I know is Liu-Tian. So here's how Liu-Tian works. Li-Tian, sorry, Li-Tian, right. Yeah, right. Junli, right. Their Gromov-Witten, construction of Gromov-Witten invariants that Tian was involved with. So what they do is they take the bundle of holomorphic, anti-holomorphic linear maps from a tangent space to S2 to a tangent space of M. That's a bundle over S2 times M. Right? This is geometry, I feel.
So
right?
Now how they choose the individual bundle.
How they make the bundles.
And then,
Yes.
Then this property, this V gamma U and so on, would, need some kind of
That gives you these, right. That's these 2 conditions, right? So, and then they take smooth sections of that bundle, right? So E is really just a finite dimensional subspace in this. Right? So you actually really only make the choice of one finite dimensional subspace. And then there's a way of spreading it out, of making a bundle, namely over all U near our representative F, we take these anti-holomorphic linear maps and restrict them to the graph of U, which lies in here. Right. And you can choose that so that you have transversality at some point, and you have transversality nearby, and so that, And magically, these guys transform nicely. So they transform nicely under this pullback here. This is a good thing, right? Yeah. So magic, right? I think that's somehow, Right. It comes from exactly. It comes from something global, but now you got to do the same thing. Right. Yeah.
Well, they are anti-holomorphic because it's a targeted to their one. Yes. But it's just, other people do other things. There's things for Mises construction. And it's very easy. Well, perhaps you want to say.
Yeah. So I just want so when you now, right, so you see that S2 here, what that really is a part of the universal curve over Deligne-Mumford space, right? Because we're gonna get W in the gamma W's, and so once we want to glue, we need to actually work on Deligne-Mumford space. So somehow we need this. We need a universal curve on Deligne-Mumford space. So we're gonna just replace this by the universal curve on some Deligne-Mumford space with, in this case, 4 marked points, and pull back sections from there. And that means that once 2 of these points coincide, we're not going to have a definition of our fiber.
Well, there'll be a bubble. The trouble is Deligne-Mumford space would have a bubble. You could deal with it. I'm sure you could deal with it. It'd be a little bit more.
It was,
Seems unnecessary.
yeah.
Actually, it's 5
5. Infinity, right. There's infinity also. Right. Sorry. Right. Yeah. So,
But it gives a very nice construction even for nodal domains, because your domains can all be put together in a little bit of you stabilize the domain and then
yeah.
you add lots of extra points.
Right. So,
And everything is going to, I mean, this is actually Liu Tian's picture, and they don't talk about some charts, but somewhere, I talked to Fukaya about this when I was sort of groping towards this construction, and he said, aha, look at appendix such and such in our book, and they do say some words about this. They say like half a page about how you might do this, but of course they don't go into any detail, but they do give this idea of how you form a sum chart.
right. But what they forget is that you still need to satisfy these special requirements. So their way of picking a space and spreading it out will not satisfy these requirements.
Yeah, but the point is, you have to understand is, there's the way of
So
Fukaya Ono in their first paper, and then there's the way of certain appendices and certain versions, and
yeah,
that's the latest version of FOQ,
maybe.
which I think.
No, no. The latest version of FOQ also has parallel transport,
Oh, it does. Okay.
and the latest version of FOQ. I mean, neither Fukaya Ono nor FOQ ever make a difference between representatives and actual maps. And of course you lose a lot of subtleties that way, And most of them, I think they just really sort of only consider the cases where the domain is stable. Because they're not worried about the other cases, and we just started worrying about the other cases and realized that that's where somehow the analytic issues come in to get you.
All right, so I think given the time,
Yeah.
move discussions to lunch.
Good.
And thank Katrin.
Thank you.